Okay, shall we start? So, hi everybody. Welcome to the next session on deep learning. So, one thing, I mean, it was not a surprise, but even not the video was recorded, not the slides. The video was not even recorded last time on Tuesday. So I posted one video which I recorded last year. Again, same thing happened last year, so I just recorded that one. So I just uploaded that one, so that should do the job, and hopefully from now on we don't get that issue. But as said before, I would always suggest that you be here because it's going to be easier to follow in person. So last time we talked about the machine learning, and we started to talk about what is machine learning, and we said it's a kind of, data-driven approach to find out a kind of relation or pattern inside the data. And then we started with a very dummy example. So we assume we don't know the Newton's law, and then we try to just find out how we can compute the distance from or the distance where a projectile hit the ground, given the height and velocity. We could do it analytically, but if we just ignore the Newton's law, then we had to do three major steps. So what are the three major steps? The first component is, so we talked about it before, data. Great. So the first component is data, so we are going ahead and collect some data. The data could be labeled or unlabeled, right? So if it is labeled, then we call the problem to be supervised. Great. So it means that we do know what output we expect to see if we give the input, and then the question is whether we can find the output for some data which we have not seen before. Yeah? So this is the data, and the second thing was model, right? So the second thing was model. So we assume there is a kind of connection between the output and input. It's just an assumption. There is no reason that it's true. But we just try to make it as good as possible so that it somehow matches the pattern we see inside the data. And then hopefully it's going to do the job, right? So this was the second thing, model. The third thing was the loss function. So we define a loss function which helps us to evaluate how good the model is working. And then at the end of the day, we try to use that loss function, or we just change the parameters inside the model so that that loss function get as close as possible to 0, right? OK, so we talked about the data. We talked about supervised, unsupervised. And then I told you that for the moment, we are just focusing on the supervised learning, meaning that our data is always labeled in this form. So we're going to have some input x. And then for that input, given to the, when we give this input to the environment or whatever it is, it's going to give us one true output, which is y. OK? That is the label. Correct? Now, what is the model then? The model is basically a parameterized function. So it's a function which has a bunch of parameters inside it. We are free to choose those parameters. But the key feature of that function is that if we give the input of the type of the data we have, it's going to give us the output of the type of the label that we have, right? So if the label is, for example, a real number, then and the input is a vector, then it's going to get a vector as an input, and then it's going to return us a real number, which is of the form of the label we have. Clear? So that is the only thing that we need to know about the model. So a function with parameters which connects the input to the output. For instance, in the dummy example we had, the output or the label was the distance that the projectile hit the ground. That was the label. And this was a real number, right? So this is the thing that we wanted, the output. And the inputs that we had, it was a vector, right? The vector of the velocity and height. And we just multiplied every entry of this vector with one weight, and then summed them up. So this is an acceptable model. Why? Because it's getting a vector of dimension 2. It's giving back a number, one scalar, right? And then this is OK. Yeah? And now I have a bunch of parameters here, and the parameters are the weights, which I can easily modify, right? So this is the model. So we talked about this. We call this model to be linear. So we talked about also difference between the linear model or linear function and affine function. They're basically linear transforms. The only difference is that in the affine case we have bias. So this is a bit of a more general case, right? So we can add one extra parameter when we talk about the affine function. So we talked about these guys, how we can extend it to the vectorized form, and now let's just get a bit more serious with the model. So the model going to give me a label, takes the data as the input. This was the linear model that we considered in our example. We didn't consider the bias. We could potentially consider the bias as well, right? But there's no reason that I would think of linear model, right? I can go for more weird models. For instance, I can go for a polynomial model, right? So it means that I get I get my input, I consider it with power 1, which is x itself. Then I take every single entry to power 2, and I keep it as a second copy, to power 3, third copy, and so on, till power p. Okay? So I have p different copies. I multiply each of them with one weight vector. Okay? So W1 is one weight vector, which gets multiplied with x itself. W2 is the second one, so on. They could be different weights. Yeah? And I can add them up all together. This still gives me one real number, right? So I still get a real number at the output. At the input, I still give my data vector. So it's still a valid model, right? So one thing here from now on, whenever you see this notation, 1 vector to power 2, or any function operating on one vector, I simply mean that the function is operating on every single entry. Okay? So don't need to complicate things. If it is a different thing, I'm going to indicate it. Okay? Clear? So you got the idea what is this polynomial function? How it works? Bias is what? Is a parameter as well, right? And it's a scalar here, right? Because the vector, I mean, this is a vector inner producted by another vector, right? So it's going to give you a scalar. So all of those terms are scalars, so it's a summation of a bunch of scalars. You know? But that bias is a parameter. Again, you can design it, of course. So, any questions? No question? So I got a question. What are the parameters that I do have in this polynomial model? B is a parameter, of course. We just talked right now. All the weights. Anything else? Sorry? The degree, yes, the p-value, exactly. Sorry, I didn't get. So p-value is still free to choose, right? So it's again a parameter, right? Anything in this model but the data that you have is a parameter, correct? Okay, so I could even come up with some more weird model. For instance, this one, if you remember the example we had last time, the projectile example. So we concluded that this D, which was our label, equals to, it was gamma, some constant, so it was roughly 0.45 times V times the square root of H, right? Now, this model is going to, this model is able to fit exactly to the true function. And I hope that you are seeing it. But if you don't see it, just simply assume that X is V and H. And then in that model, I can set W1 to be 0.45, 0, and W2 to be, W2 is the one with the square root, right? So it's going to be 0, 1. Now, if you replace this inside that model, what's going to happen? You get exactly the equation, right? W1 times the inner product with this guy. It's going to be 0.45 times V plus 0 times h, right? Which is going to be 0.45 v. So here, W1 transpose times x is 0.45 v, right? And then what about W2 times the square root of x? It's going to be 0.1 times the square root of v is square root of h. It's going to be a square root of h, right? And then you multiply these two guys together. Then out of this, you're going to get your y equal by 0.45 v the square root of h, correct? So this y, the label that your model, or the output that the model gives you here, is exactly this d when you set your weights to be this specific combination, right? But if I set the weights to anything else, this is going to be some other function, correct? But I could only come up with this choice if I had some intuition from very beginning. I mean, I knew that distance is related to v itself and the square root of the height, and then I just wrote that model, right? So I have seen some pattern. I assume this model, and then I just fit it to the data I see, correct? So assuming that I know that, for example, the distance is proportional to the velocity, is proportional to the square root of the height, but I don't know exactly what is the gravity of the Earth, I can simply do it. I mean, I put this model, and I collect data, and I fit it to the data, and I'm going to get, hopefully, the right coefficients, right? So that is what you used to do in the physics lab, right? Great. So you can come up with any sort of model, so there is no reason that you have one specific model. But in this course, we are always going to deal with neural networks. And we're going to see why, because they are very powerful models. They can pretty much do anything that we want. But in general, as I said, these models are only functions which have a bunch of parameters we can design. Those kind of parameters could be of two different forms. They could be either hyperparameters or learnable parameters. Okay? Now, what is the hyperparameter? The hyperparameter is the parameter that I need to fix before I would be able to write down my model explicitly. So think of the polynomial model. Can you think of any hyperparameter there? P, exactly. So if you don't know what is the order of your polynomial, so here in the polynomial example, if you don't know what is the order of the polynomial, you cannot write down your model, right? So if I tell you the order is, for instance, 2, then you're going to say, OK, then I'm going to have a bias. I'm going to have one vector of weights, W1, which is going to get multiplied with x. And I'm going to have the second one, which is going to get multiplied with x squared, right? If I don't tell you what is p, you cannot write it down, right? If I tell you a general p, then you cannot write it down. Clear? So this is something that I call it hyperparameter. So I need to just specify it in advance in order to be able to write down my model explicitly. Clear? Right? OK. So you might ask this question that how can I tune this guy? Because potentially, if I choose different choices of p, then I'm going to conclude different solutions to my question or to my task, right? But the point is that, I mean, this is a kind of a specific thing we're going to do later, OK? It's not it's itself is a kind of lecture, OK? But for now, you don't think about it. You assume that there exists a genie, and then it tells you the good choice is, for instance, 2. And you're going to go ahead with that. So you would never deal with tuning a hyperparameter when you are doing the training. Hyperparameter tuning is something that you do later. I mean, you just need to do a sequence of trainings to understand what is the good choice of the parameter. But for now, we assume that it's given to us. So any hyperparameter in the model, we are free to choose, but we need to choose it before we start the learning process. Clear? Any questions? No question? Great. So what about the learnable parameters? They're the weights, exactly. So once you fix the hyperparameter, then you can write down your model explicitly. And anything remained in this model that you can tune is what we call it the learnable parameter. For instance, if I set p equal by 2, then I do know that I have one bias, two weight vectors. And the only thing remains is that given my data set, I try to find the right choice for the weights and bias. So weights and the bias are the learnable parameters. Clear? Everybody's clear? Any question? Great. So now, say I fix the hyperparameter to be 2. Now I do know what are the learnable parameters. And then what do I do then? I have the model fixed. I have my data also with label. The only thing that remains is that I get x, put it inside the model. I look at the output, try to play with all of those learnable parameters, the weights and bias, in order to make that output be approximately the label that I see inside my data set, right? So this is the whole thing remains. So I only need to do, the whole learning process is to find some good choice of these weights and bias, such that for every single guy inside this data set, when I give x to the model, I see approximately the same label, or the same output as the true label that I have inside the data set. Everybody's clear? Yeah? So now, if I want to do that, there are a couple of things unclear here. The first thing is that, say, I want to do this, right? I want to have approximately my output to be this guy. But what do I mean by approximate? Huh? Sorry? Difference is 0. If the difference is 0, then it's exact, right? It's equal. Yeah? What do I mean by being approximately equal? So it has some intuitive meaning, but I need to formulate it if I want to really do it, right? And this is where the loss function kicks in, right? Yeah.
The error is smaller than some structure.
Sorry?
The error is smaller than some structure.
Yeah, you could say it, but how do you evaluate the error? How do you compute the error? Sorry? The difference, yes. But what is that difference? Difference, you always think of two numbers. What is the difference between two numbers? Is their subtract, you mean? No, not always. Yeah, you might think of that. Like, so 5 and 1 are more different than 2 and 1? Not always, right? So it depends, correct? So sometimes you would say 5 is here, 1 is here, is too much difference, right? But 2 is closer. This is one point of view when you can interpret your output y in that sense. But if that 1 and 5 and 1, 2, and 5 are cat, dog, and frog, then cat going to be dog or cat going to be frog going to cause you the same mistake, right? So you cannot say 2 is much more different than 1 as compared to 5 and 1, right? So this is not always the case. So this is why we define something called loss function. Yeah? And your intuition is 100% correct. You think of y as a real number, and then you would say, OK, I try to get as close as possible to this number. But not always y is a real number, as we're going to see in the example of classification. And also, it's not always the case that we want them to be close to each other in value, maybe in some other senses. OK? So moral of the story, once I have my model, the only thing that I want to fit my data into that model. But in order to be able to define what do I mean by fitting the data, I need to have some metric, some measure that make me able to just compute how different my output is from the true label. OK? Now, this is what we call it loss function. And once we know loss function, then the whole thing is over. Because we have the loss function, we can compute that difference. and the only thing remains is to minimize that difference. So let's just get to the loss function. So the loss function in general is one function that takes two different inputs. One of them is the output of your model. The other one is the true label you have inside your data set. It's going to take them, compare them against each other, and then it's going to give you one number, usually non-negative, to just tell you how different they are. Okay? So if this is, if I consider my polynomial model with the hyperparameter p equal by 2, then I'm going to have these three learnable parameters. I can potentially set them to be some specific numbers, right? Say, for example, this w10, I set all of them to be 1, for instance, right? So if I put all of them to be 1, then once I give one of my data inputs, xi, one of the data samples from my data set to this model, I'm going to see some output z. Is z necessarily exactly the label that I want? No, z is not y, right? Because if I want z to be y, I should find the right choice of the weights and bias, correct? So z is potentially different from that guy. So the thing that loss would do for me is that it takes this value of z and then compare it against the true label y. Clear? So loss is basically going to look at z and y and give me one number, as I said, usually non-negative, because we usually think of difference to be either nothing, 0, or something more than 0. Some non-negative number usually, but potentially it could be any real number. And then it's going to compare these two, give you that number to just quantify the amount of difference they have. So as your friend said, you can immediately think of this guy, right? So you would say, I get z, I just subtract it from y, this is the difference, I want to make it non-negative, so I just take it to power 2, right? So this is a very intuitive approach to quantify it, right? But not always this is the case, right? So for instance, you can go, this is what we call it the square error function, okay? Meaning that it takes two numbers, calculate the subtraction, and then square it, yeah? So this is one kind of error. But you can have also error indicator, yeah? So I'm going to look at z and look at y. If they are the same, I'm going to put number 0, meaning that there is no difference. But if they are not the same, I don't care how much they are different. I'm going to say they are just different, so 1. Yeah? It's like I detect an error. And this is usually the case when you do classification, right? So if the output of your model is telling you cat and the true label is cat, no error has happened. But if the output of your model is anything but cat and the true label is cat, then you're going to have error. And you don't care what that thing is, right? Everybody's clear? So this is going to be the loss function. And once you have the loss function, then everything is over. You have basically all the three components, right? You have your data set. You have your model. So this model is going to get the input sample and then gives you one output which is similar or in nature as your label. And then you have a loss function which can compare the output of your model and the true label. So as I said, we're going to think of supervised learning here. So we always have the label. And here, I am going to use this notation from now on, time to time. And by this model, I simply mean that, by this notation, I simply mean that this is a function. This function could have some hyperparameters, so I'm going to show them by h. But when I want to start the whole learning process, I'm going to make my mind about h, right? I'm going to choose one value for h, put it there. And then this function f is going to be only dependent on x and the weights, correct? Everybody's clear? So this is going to be the function then. And then my loss is going to compare the output of that function with the true label that I have in my data set. Any questions on that? No question? OK. So if you got no question, then let's go for the idea of training. So what is the idea of training? So the idea of training is that if I want to do the training, I basically want this model that I have to be tuned with a bunch of learnable parameters, such that those parameters are now mimicking what is happening inside my data set. Meaning that this function, after being tuned, is able to just get one data sample and give me the corresponding label. That is what I want. But let's say that I did it for every single guy inside data set. So I just made fit this model into the data exactly. Meaning that every single guy inside data set that I have, every single of those xi's, when I give it to my model after doing the tuning, then I'm going to get the output, which is exactly the label. Say that happened. Okay. Can I guarantee that this model is now capturing everything inside the environment? No. I cannot say it, because it might be that I get a new data, x new, and I pass it through that model after doing the whole training, and then I look at the output, and it's not the true label, right? Because I had not seen this particular sample when I was doing the whole tuning, right? So what I wish for is that I'm going to do the tuning, not only that my model fits the data that I have, but if I see anything in future, it's going to fit the true label as well. This is the idea of generalization. And the whole key point inside machine learning is that we are looking for generalization. It means that I want to get trained on a bunch of data, but whatever I conclude as the trained model, whatever I learn as a model, it's going to in future predict the correct labels for me. Clear? So this is the idea of generalization. And in order to get that, the only thing that we are going to do is to train the model. So the idea of training the model simply means that I am going to tune those parameters, given the data that I have, with this perspective in mind that in future I have a good output. Clear? So this is the whole idea of training. Now, if I want to just specify the training, I need to just walk you through a tiny bit of analysis. But before we start with that, I just want to give you one example, the example of classification, which is going to help you understand all of these definitions we had up to this point better. So any questions? Did you get the idea? What is training? What is the model? So none of these terms sounds like weird anymore? Everybody's good? Great. Cool. So let's just go ahead with the example of classification. So what is the example of classification? So these labels that we have in our data set, as I said, I mean, for now, assume that those labels are simply scalars, okay? Just single number. That single number could either be a continuous real number, or it could be integer number, right? Or it could be anything else, right? So now assume that this label is only integer, okay? So it could be either C1, C2 till Cj, yeah? Finite number of cases. Then the problem is going to be called problem of classification. Why? Because I assume that every single data inside my data set has a label which is one class, right? Class C1 or class C2 or class C3, so on. So basically what I want to look at a bunch of data and then be able that in future when I get a new data, I specify what is the label. It means that I specify what is the class, so I be able to classify it. This is the problem of classification. So we have it quite a lot in the, all of you had it at some point in your undergrad courses. Usually you used to do it not with machine learning, like analytic way, but this is the oldest problem we can think of in terms of artificial intelligence, one of them at least. So one example is the problem of image classification. So when I talk about image classification, the data that I have inside my data set is in the form of images with labels, right? And that label is going to specify that this image is belonging to which class. For example, the classes are cat and dog. So I only have images of cat and dog inside my data set. So it means that I collect a bunch of images. Each image is either image of cat or dog. So I take the first image, I put it inside my data set, and I write in front of it dog. The next one I write in front of it cat. This is the label, and so on, right? So this is going to be a supervised learning problem. The data is your image, the label is cat or dog, and then this is the problem of classification because I have a finite number of classes as the label. Clear? Now, I can write this problem down in numerical form. Everybody agrees, or yeah? So I do know all of you know that, but as I said, I consider myself in your situation, not your situation, like sitting here listening to the first lecture in deep learning. So I'm going to just be a bit more concrete. So let's see how we can, it doesn't harm that we try it once, how we can represent the whole data set in form of numerics. How we can do that? So if I have one image, all of you know that this image could be written in form of a matrix of pixels, right? So for the moment, assume that we have a gray image, meaning that every pixel is just changing between pure white to pure black, right? So some gray range between these two. There is no RGB image here, so you don't see the color is either white or black, or something in between in terms of intensity, right? So if you have one image, you can just think of it in form of pixels, right? And then you can think of it in this case for a gray image. You can think of it in form of a matrix, and every single entry inside this matrix is one pixel value, right? Those pixels, you usually save them in form of with finite number of bits. So do you know what is the classical number of bits we use for every pixel? Any guess? 256 is not the number of bits, number of cases, right? So we use 8 bits, right? And if you have 8 different bits, how many numbers you can show with it? 256 different cases, right? All of them 0, then the first 7 0, last one 1, then all of them 0 1 0, and then so on till the case where all the 8s are 1, right? So you do have 2 to the power 8 different cases. This means that if you want to show them in form of integers, you can say is 0, 1, 2 till 255, right? So every single pixel inside this image is either 0 or 1 or so on till 255. And depending on that value, you have a different intensity or mixture of white and black, which makes the gray color in it, right? Clear? So if I think of the image, I can write it down in form of a matrix of pixels. And I can just throw away the whole image and just keep the matrix of pixels, right? Now, I can get this matrix of pixels, and I start from the very top left entry and write it down in form of a vector, right? So the first entry is the first entry in the vector. I keep on going, for example, the first column. Then when I get to the second column, then I put it below the first column and keep on going, right? So if I have, say, one image which is 10 by 10, how many pixels do I have? 10 by 10 image, how many pixels do I have? 100, right? So I have 100 different values for the pixels of this image, and I can put them in one vector of dimension 100, right? So my image could be represented with very, very long vector, but it's still a vector, right? And every single entry inside is either 0, 1 till 255, right? And if I'm not happy with those big numbers, I can divide the whole vector with 1 over 255, right? And then everything going to be between 0 and 1, correct? So I'm going to have a very long vector, and that long vector can just represent my image. That's it. So my image is nothing but a vector, which I'm going to call it the pixel vector. Okay? Every single image that I get is, at the end of the day, a pixel vector. It could be a huge vector, but it's still a vector, right? So that is the kind of data that I have here. And then what about the labels? The labels are either cat or dog, correct? So I'm going to make an increment. So if it's dog, I'm going to say the label is 0. If it's cat, I'm going to say the label is 1. Correct? And if I do that, then I can represent this whole data set, which I capture from the environment. I went out, I took pictures, I got the picture, I look at the animal, I said this is cat, write it back of the image. So I can just represent that in form of a set of numbers, right? And this set of numbers has lots of pairs in it, I different pairs. Every single pair has one x, which is basically the pixel vector of my image, right? x1 is the pixel vector of the image number 1. And that number, that integer next to it, which is either 0 or 1, it's just indicating what kind of image that is, right? So if it is 0, it simply means that this is an image of dog because I made this increment at the very beginning. Everybody's clear? So image classification, again, you can write your data set exactly in the form that we started with when we were modeling the data, right? And now, I have this, I want to do learning on that. Meaning that I get this data set, I get this numerical data set, and I want to design a model. This model should get this pixel vector, and then it's going to return me one number. What should be that number? 0 or 1, right? As long as that model has this property, is an acceptable model for me, right? And then I leave a bunch of parameters inside the model, free to choose. And I try to do it such that for every single image inside my data set, it's going to give me the right class. Once I did that, then I go and take a new picture of a cat and give it to my model and check it, whether it's going to give me still the label cat or not. Clear? And then if it still works fine, then I would say, OK, my model is generalizing. So the whole story is that. So what I want to do, I want to get this particular data and any pixel vector, and then I want to get at the output of my model one label, which is either 0 and 1. This is the problem that we call it binary classification. It is classification, I mean, it's obvious, and then it's binary because the label is binary. It's either 0 or 1. OK? Everybody's clear? And the model that I choose, which gets the pixel vector in this case and give me 0 or 1, this is what I call it usually classifier. So don't I have it here? OK, it's in the next slide. OK. Now, this binary classification is a kind of very primary problem and very fundamental. And it has multiple reasons. One of the reasons is that, as I told you, classification is one of the first things we were looking into as human beings to be done by machines. Yeah? I mean, I don't know your background, but I'm pretty sure every one of you had always had this kind of problem that you're going to see some, in any engineering field, you're going to see some observation, and you want to know where it comes from, right? Like those people who do communications, signal comes and you want to detect what was the message being sent, right? And if the message was bit of information, it's either 0 or 1. Yeah? So you basically see some noisy observation out of those wireless signals coming to you. And then you basically, out of that, you want to find out what is the true label. Is it 0 being sent or 1, right? In other mechanical environments as well, right? So this is a very old problem, one of the first problems that not only with analytic models, people in machine learning, people in data-driven approaches also started to work with. And one other thing is that even though it's binary, but you can always extend it to any number of classes. So what if instead of 2 classes, I have 3 classes? Not only cat and dog, but I have cat, dog, and car. What can I do? I can write it down in forms of 2 binary problems, right? So I could just have one binary classification. I would say class 0 is dog, class 1 is cat or car, right? Then I do the classification. If my classification is successful, then if it is dog, then I stop. So this is dog. If it is not dog, so it means that it is either cat or car, right? And then I go for the next binary classification. I would say, OK, now whether it is cat or dog or car, right? So again, another binary classification, and it's over. So if I can solve the binary classification, I can solve any other classification as well, right? So any M-class classification could be written as a sequence of binary classification. But this is not the way we do it in this course, of course. Yeah? We're going to find a more sophisticated way to do that. Now, let's just look at this problem and try to build the components. So the first component, as I told you, was the data set. So the data set has input, which is the pixel vector, the label, which is your binary number 0 or 1, specifying the class. And the next thing that you have is the model. Yeah? And as you said, the model should be able to get the pixel vector and give you at the output one binary number, right? So can I use a simple linear model to do that? What was the linear model? What was the linear model? So in the linear model, I consider my label to be one vector multiplied by the input, right? Correct? So if this guy is a pixel vector, and for the moment you don't need to think of those 8 bits or other things. Okay? Just think of it to be one real number between 0 and 1. Every single guy inside it is between 0 and 1, for instance. Okay? It's a good approximation. Then if this is the case, then if I get it multiplied with a vector of weights, which are again real numbers, what do I have here? A real number. Could I use it as a model for classification? No, because it's not giving me a label that I want, right? A label that I want should be binary. What can I do to that? Yeah, just go ahead. You can define a threshold. You can define any function, any scalar function that gets a real number and give me back a binary number. And if you add it to this model, it's going to be a valid model, right? So one thing that we are going to do, so any model of this form, which is getting the input and give you back an integer class of or finite number of classes, we usually call them classifiers. So classifier is not a term coming from Mars. It simply means model, okay? Which is used for classification. Now, what I'm going to do, I'm going to use perceptron, which is one of the very first models being used for classification. Okay? And what does this model do? This model is going to get x1 to xn. So this is the entries inside your pixel vector. Every single entry is going to get multiplied with its own weight. And then they get summed up here, added with a bias. And then it's going to give me one number, z. How can I write down that z? Can you tell me how can I write down this? How can I write down the z there? How can I write it down? It's going to be the summation of all of those weights times x's, right? Plus the bias. And this is running from 1 to n, exactly the number of entries I have in my input. What is this guy? What kind of product is it? Is it an outer product? What is it? It's an inner product, right? So I can think of this w to be a vector, so I can write it down in this form. I can say I have w1, w2, and so on till wn multiplied by x1, x2 till xn plus my bias, right? This guy getting multiplied to this guy, it simply means that I multiply every single entry and then I sum them up. This is the same term here, right? So let me just call this guy to be a vector w, this guy to be a vector x, and then what I have is basically wx plus b, which is a affine function, right? So this guy here, this yellow guy here, is an affine function. Everybody's clear about that? Yes? I mean, it's 3. Why you're not so tired? Or you're tired of me. I mean, you had too much of me this week, right? So it's going to be the last hour. So now, everybody's clear about that, right? So this yellow thing here, z, is an affine function in terms of x. Yeah? Okay, so this is what we call it. This is the affine transform. These w's are what we call them weights, and b is the bias. So we are basically computing one affine transform or affine function of the input, and this is going to be z. This z is a real number, correct? It's a number which could be between minus negative to plus, minus negative, oh good, minus infinite to plus infinite, right? Theoretically, right? Now, but if I look at the sign of this number, what should be the sign? Sign could be binary, right? I could, for example, make this increment when the number is negative. I'm going to return 0. This is what you see here. If z is negative, I'm going to return 0. If z is positive or 0 itself, I'm going to return 1. Clear? This is what you know it as step function, correct? So this guy is the step function, so I can put one step function here. I'm going to show it by s. And then this y is now going to be a binary number. Clear? So this is what we call it perceptron. This was proposed initially by Rosenblatt. I mean, not by Rosenblatt. It was initially proposed by Pitts, but then developed into a kind of computational model by Rosenblatt. 1957, I think. We have it in the slides. So, but anyways, this is, for us, it's simply a model, right? So it's a model which gets one data of the form that we have, a pixel vector, and it's going to return us one binary number. This is exactly what we want, right? Everybody's clear? OK. So I'm going to show it compactly in this form because we are going to use it a lot in this chapter and the next one. So this is going to be the model of the perceptron. So you get different inputs into it. Everybody has its weight. And then you're going to add a bias, just threshold it, check the sign, and then the output is going to be a binary number. OK, any questions? Yeah.
When you do the step function, when you choose z greater or equal or smaller, is that all customized? Can you choose another threshold?
Of course, definitely, yeah. I'm going to talk about this. Yeah, you can definitely choose another function, of course. This is just because Rosenblatt did this. Yeah. Any other question? Clear. OK. So this is what we call it a linear classifier. Why we call it linear classifier? Because before we start to just decide on the sign, we just did a linear transform. But this is not the only reason. I'm going to show you a more intuitive reason for that. But this kind of classifier is what we call it a linear classifier. We get the input, we compute a linear function. Out of that linear function, we decide the label, right? So this is why we call it a linear classifier. So we have a linear transform, and then we classify everything at the output based on the sign of that linear transform. So the only information we collect is that linear transform, right, to do the classification. So if I want to write it down mathematically, we already did it on the board. So y, I can write it down as the step function of sum of all of those products, weights and pixels. And then we add up the bias. So I can write down this guy in this form. So I can say w is a vector collecting all possible weights. And then x is the pixel vector. And then the inner product of them is exactly this summation here. And I have the bias, so I can compactly write down my model in this form. So step function of a linear transform. This would be my model. You got a question? No? Okay. Any questions? Everybody's clear? Great. So that is my perceptron model. And now here in this model, I have a bunch of parameters, right? Do I have any hyperparameter here? Do you think I have a hyperparameter? The step function could be. That's good. I mean, the idea that I have chosen a step function to do that, this is a kind of hyperparameter. You're right. I mean, it is not what in practice we usually think of as a hyperparameter. Usually as a hyperparameter you think of a number, but you are totally right. The fact that I'm using a step function to do this classification after doing the linear transform, this is something that I have chosen, right? I could do it differently. I could say, why only the sign? Maybe instead of a step function, I just get that z. What is this z? This is the affine transform, so W transposed x plus the bias. This is what I have computed after the affine transform. When I get this, right now what I'm doing like this. So this is the step function. This is the this is the step function, right? So the step function, I'm going to look at z. If it is negative, it's going to give me 0. And once it is positive, it's going to give me 1, right? So this is the step function, s of z, and here is 1, right? But what should I do that? Maybe I could have done something else. Maybe I could have had this other function, which looks like this. I don't know. I'm going to call it QZ, right? This is still giving me at the output 0 and 1 only, right? So it's going to look at this z. If the z value is somewhere between, I don't know, for example, threshold 1 and between minus infinity and threshold 1, or threshold 2 to plus infinity, it's going to give me the output 0. And if it's anything between t1 and t2, it's going to give me the output 1, right? This is still a valid model, correct? So if I replace s here in this model with q, this is still going to work. It's still doing the binary classification that I want. Yeah. So it was my choice to choose this step function, correct? So because of that, this step function is a sort of hyperparameter. As I said, this is not something that you might probably think of. You think of a number. We're going to do that as well later when we get into a deep neural network. But conceptually, this is again a hyperparameter. I need to specify it before I start the whole learning process, right? At the end of the day, I need one function here which gets this real number and give me a binary number. Yeah? I cannot do anything before I specify that. And this is why it is a hyperparameter. But that aside, what is the learnable parameter here? The weights and the bias. Exactly. So weights W and the bias B, they are the learnable parameter. And this is usually in the nature of any practical model that we have. They are, all of the learnable parameters are in the form of weights and biases. Okay? Any question? Everybody's clear? Great. So if you got clear, then let's have a quick break. So it's now 3:03. So we're going to have 5 minutes, and then we just keep on with the linear classification. Exactly. So it was like the model is y equals w1 transpose times x. The whole thing multiplied with w2 transpose times
So from here, this big n notation refers to that in the future. Image one, the image pixels you see.
like, for example, 28 by 28 can be seen in So, shall we go on? Okay, so the perceptron, this linear classifier, it has a sort of nice geometrical interpretation which helps us understand why we call them linear classifiers. So if I want to just make it clear for you, let's just look at the simple case where we have two-dimensional input. Okay? So my input, it could be only x1 and x2. I mean, it has two different entries, x1, x2. And it's given to this perceptron. This perceptron, what it does, it's going to multiply every single of those entries with their corresponding weights, add them with a bias, and then check the sign, right? And then it's going to tell me whether it is labeled as 0 or 1, or it's classified as 0 or 1. Clear? So this is easy. We can simply plot it in the two-dimensional space. So if I want to just write down the whole perceptron, it's going to be the step function of this linear transform. So the linear transform is of this form. So what it basically does, it just look at this linear transform, this guy. And if it is non-negative, then it's going to be 1, the output. The class is going to be 1. And if it is negative, the class is going to be 0. Correct? OK. Now, let's see how we can show it in 2D. So if I want to think of it in 2D, so I have this expression here, this W, the weights times x's plus the bias. What is that in two-dimensional space if I set it exactly to be 0? What is that term? W1 times x1 plus W2 times x2 plus bias b equal by 0. What is it in the space of x1, x2? So if I think of x1, x2, so I have two-dimensional space. The horizontal axis is x1, the vertical axis is x2. If I set this line equal by 0, what do I have in this plane? I'm going to have a line, right? How can I draw that line? Let's say everything here is 1. I mean, these weights are 1. So say W1 and W2, both of them are 1. And B is minus 1. So here I have written weights are positive, the bias is negative. This is fitting what I've written there, right? Weights are positive, bias is negative, correct? Now, if I do that, this means that I don't have W1. It's just 1. Here, W2 is 1. And this bias is minus 1. And if I want to draw that line, what should I do? I can say one possible point is that x1 is 0. X1 is 0. Then x2 should be 1. So this is one possible point. And now, if I said x2 to be 0, so x2 is 0, what should be x1? Again, it should be 1, right? So it is 1 here and 1 here. And then what do? I just connect these 2 points, right? And this is the line. Every single point on this line, when I put it inside this expression, it's going to give me 0. Clear? Everybody's clear? So I have this line, as long as the bias is negative and weights are positive, then it's going to look like such a line, right? So it's going to meet this vertical axis and horizontal axis on the right-hand side and top part. So it's going to be of this form. This line, any point on this line, any point x1, x2 on this line, when I put it inside that expression, it's going to give me 0, right? Now, what if I look at one point above this line? Like here, for instance, one point here. Say this point is 1 and 1, okay? What if I give this point into this line? What's going to happen? It's going to be 1 plus 1 minus 1 equals by 1, which is more than 0, right? Okay? So what if I give this point, 2 and 2? What's going to happen? Would it be positive or negative? Positive. Anything here is positive. Any point in this part, if I give it into this line, the term that I get is going to be positive, correct? So any guy at the top of this line, if I give it to that expression, it is going to give me a positive combination, linear combination, correct? So it means that when it goes inside my perceptron, any point in that part of the plane, when it goes inside my perceptron, it's going to give me as the label, the perceptron going to classify it as 1, right? Because the perceptron is going to look at the sign of that linear transform, correct? And the sign of that linear transform for any data sample that is inside this part of the plane is going to be positive, correct? Everybody's clear? Great. Now, what if I give a point in the lower part of this line? What if I give this point, for instance, 0, 0? What's going to happen? It's going to be 0 plus 0 minus 1. It is minus 1, which is smaller than 0, right? It's negative. Any point here is going to give me one value, which is negative, right? It's not 0, it's negative, right? Everybody's clear what I'm doing? Yeah? You know, you can always ask. Everybody's clear? So any point below that line is going to give you one negative linear combination, one negative linear transform, and that negative linear transform, when passed through the step function inside your perceptron, is going to be classified as 0. Just 45 minutes more you need to wait to stand me, and then I'm going to be dismissed. So everybody is clear? Yeah? So this is the part of the plane. Every single sample from that part, when it goes inside your perceptron, is going to get classified as 0. Clear? Now, what can I say? So what is my data? Any data sample that I have, it's going to be, I told you that x is in 2 dimensions, right? So it means that any single data point that I have is going to be one point in this plane, correct? Yeah? So that point, for instance, you can think of a 2-pixel image. It's a very stupid image, but this is still an image, right? So this could be an image. One of the images that you have is one point, in a very high dimensional space. And that point is going to be either on top of this line or below this line, correct? Or if you think of a very high dimensional space, instead of a line, you're going to have a hyperplane. And this hyperplane is the collection of the points where you have every single point inside that on that hyperplane going to make that linear transform 0. So any point that you think of is either below this hyperplane or on top of that hyperplane. Okay? In 2D, that's easier. Anything is either below the line or above the line, right? Now, what you want to do, you want to have that line aligned somehow that when you have any image of dog, then it is going to be below the line, so that it's classified as dog, 0. And any image of cat that you have, the corresponding point is going to be above that line, so that your perceptron is going to classify it as 1, which is cat. Clear? So this is what you want to do. And how you can do it? Adjusting weight and bias, right? So the only thing that you can do is that you get this line and play with it, right? So you just push it up, push it down, I don't know, you rotate it. Any of that things you can do by changing those weights and bias, right? But you cannot do any nonlinear behavior, correct? Whatever you choose as the weight or bias, it's going to be at the end of the day one line, and anything below the line is dog, anything above the line is cat, correct? So this is why we call it linear classifier. This is the geometric point of view. And this is going to help us a lot when we want to just go for neural networks. Any questions? Everybody got clear? I mean, I do personally, when I was like young, not old as I am now. So when I was a student sitting at your place, I remember many people used to just show it like this. So they put some points on the plane and just draw a line, and they say like, here is a linear classifier. But I never understood why they just immediately do that. Okay? I hope that I was not one of those people. So I hope that you got the idea, what do I mean by linear classification. So, but as I said, you always can ask questions. Yeah? Any question? Great. So now this perceptron was one of the very basic things that people started to come up with when they wanted to do artificial intelligence. At that point of time, they did not call it artificial intelligence, but it was one of the, say, first things that started to work for some, data-driven algorithmic approaches. So it was proposed by Rosenblatt in 1957, and then 1 year later he wrote a paper, which I think I put the report inside. You can go in the further read part of the Kirkus page, and you're going to see the link. I think I put the paper itself. So you can read the paper. I mean, it's typeset like with this type machine. It's very old report, but you can see what he has done. So he came up with this idea, but to be fair, this was not his original idea. It was Pitt's idea, where he was working around 43 on the idea of describing a biological neuron so that with a mathematical model, so that that model is somehow capturing the pattern that is being done by the biological neuron. So a biological neuron, people, I mean, at least the understanding we have from it is that it's going to sense some sort of signals out of the end nodes on the neuron, and then based on the intensity of those signals is going to be either activated or not activated. Okay? So this was the idea. So anything is happening inside our brain, like if I touch something, there are lots of neurons which are going to be, there are some signals being like activating the output of that neuron, and then that neuron is going to activate the other neuron, and this is how I start to sense things. I mean, this is at least the illustration we have for this biological component. And then at that point of time, they were interested to see whether they can model it as a kind of mathematical model. This perceptron, in a bit of more details and with more math, was somehow considered to be a kind of mathematical description of that biological neuron. And this is why nowadays we call it neural network or artificial neural network, because these guys are some sort of artificial model of the real neurons that we have. Okay? Clear? So this Walter Pitts, probably the one who was behind the whole study. Probably you think that he was a professor or something, but he was not. He was just a researcher, and he was just interested in logics. I think he never got a very sophisticated degree. It doesn't mean that he couldn't do it. He never wanted to do that. And he even did not get employed by MIT, even though he was working at MIT for a long time. And the reason was that he never wanted his name to be public. But still, nowadays we know him, right? So he never signed a contract because he never wanted to sign his name on any contract. So he never wanted to be known, but he's now very well known. And these neurons are being called Pitts neurons. So this is a very nice story. This was a kind of breakthrough after Rosenblatt just rediscovering this. But for us, this perceptron is nothing but a model, okay? It's a very simple model which does linear classification. Clear? But just nice history behind the scene why we call it artificial neuron nowadays. Okay, everything clear? Great. So we have the classification model, and now we can just write down the components of the problem that we have in this binary classification. The data set, once again, is collection of pixel vectors and their corresponding labels, which are binary. And then our model is perceptron, right? So it's a model which gets a pixel vector and gives me a binary number. Now, the whole thing remains to just complete the components is the loss function. Great. So I need to find or define a loss function which somehow, again, captures the difference between the output of the perceptron and the true label that I have inside my data set. So we can go for different losses. So squared error, I showed you. Error indicator, I showed you. We can use more sophisticated ones like Yale divergence. You might not know this, but we're going to talk about this later. So no worries about that. But what I'm going to do right now, I'm going to just stick to what Rosenblatt did because I want at the end of the day to just complete his own algorithm. So I'm going to use the indicator error. And this is the most intuitive choice I could have, even though you're going to see later on that this is not a good choice. It's going to make us lots of troubles. But for the moment, this is a kind of intuitive way of evaluating the error, right? So what does it do? It looks at the output of the perceptron. Also, it looks at the true label, and then it compares these two against each other. If both of them are 1 or 0, it's going to say there is no error. So output of the perceptron is same as your true label. There is no error. But if the output of the perceptron is different from your true label, it's going to give you 1, meaning that if you give your pixels to the perceptron, it gives you label 1, which means cat, but the true label is dog, then it's going to say there is 1 error here happening, right? Clear? Okay. So this is something, this is the sum loss function that we can choose, and then out of that, we can just use that loss function to just go over your data set and try to fit it, right? Or fit our perceptron into that data set. So what does it mean? It means that I can get this particular pixel vector for every single pixel vector that I have inside my data set. I get that pixel vector. I pass it through my perceptron. I look at the output. Then at the output, I'm going to check it against my true label. And then I see if it is the same one, then I'm going to say no error. If it is not the same one, I'm going to say 1 error. And I keep on summing them up, right? So I go for the next data point, till I'm over with all the cats and dogs that I have inside my data set. And then I'm going to tell you, OK, out of 100 images I tried, I had 20 errors, right? And then please go ahead, change those W's and B, and come back to me. Let me know that you have updated. And I'm going to check it again, see whether I get less error. Clear? So that's going to be it. And once I have this, the only thing that is left is that you need to find a kind of machinery, a kind of a strategy to know how you can play around with those W's, right? How should I change W next time that when you come back to me, instead of 20 errors, I have 10 errors, for instance, right? So I'm reducing the number of errors. This is the story of training. And the whole thing about the deep learning is the fact that training is hard, but that you can come up with a good training. I mean, at the end of the day, we always use backpropagation plus gradient descent, and we do the training. But this is one key factor, right? So when deep learning works, means that the training could work, and then you can come up with a very complicated model which captures everything that you want. You can train it, fit it to the data, and then this is what you see nowadays. I mean, there is no magic more than that. I mean, you have lots of parameters, and then you can fit everything. So the whole story from now on is the training, and the training is simply to tune all of those learnable parameters. It means in terms of perceptron, the weights and bias, we want to just tune them so that we have a very good fit to the data, right? And how we can do it, okay? Any suggestion before I start with that? How did we do it in the dummy example? Was it so complicated? If I want to quantify everything, so how did I do it with a projectile? When I had all of those data and I considered that linear model, what did I do then? I computed the loss. The loss was what I get out of that linear model and the true distance, right? I subtracted them, made them square. And then at the end of the day, what did I do? I summed up all of them, right? And then I said, this is a function of the weights, right? And then I went on and tried to minimize that against weights, right? So I tried to solve the optimization problem, correct? So we are going to do the same thing here, but with a bit of more math, okay? A bit of more probabilistic flavor. So before I start with that, just a recap about the probability theory. So I'm pretty sure everybody here knows this stuff, but just to make sure that we are on the same page. So a discrete random variable, it could be a finite number. It could just be one of the finite number of cases, right? One of the finite number of outcomes. And each outcome going to happen with one probability. So I'm going to show it with x. So x is the random variable, and then the probability of x, it simply means like if I am computing probability of x0, it simply means that the probability that my x be the particular value x0. The most simple example is the binary case, right? So in the binary case, in the binary case, you have your x being either 0 or 1, and each of them could happen with one probability, right? So for example, it could happen with probability half, half. So if I have one random variable x, and it's discrete, then it could be a bunch of outputs. For example, it could be 0 or 1, and then it's going to be 0 with one probability. So it's going to be a probability of 0, and one other probability for this output 1. Okay? So for instance, it could be half, half, correct? But can it be half 0.7? No. The probability should sum up to 1. Okay, it always sum up to 1. And can it be negative? Yes or no? No, it cannot be negative. Great. So what if I have a continuous random variable? Then what should I do? I should integrate, or I should, instead of probability mass function, I need to define a probability density function, right? So if I have a continuous random variable like a Gaussian random variable x, this x could be anything on the real axis, right? It means anything from minus infinity to plus infinity. And then what is the probability of one Gaussian random variable being exactly 0? The probability is? Probability of a Gaussian random variable being exactly 0. What is it? What is the probability that I just throw this chalk and it hits exactly 1 point on the ground? What is the chance? Go ahead. 0. Exactly. So the probability of the Gaussian random variable being exactly 0 is always 0. I cannot define a probability. this whole space is infinite in comparison to one point, right? So that probability is 0. What do I define instead? I define the density function. So density function doesn't say that I hit exactly this point. It says, what is the probability that I hit somewhere around this, right? So what is the chance that x is somewhere between a and b? This is going to be evaluated by that density function, right? So I'm going to integrate from a to b from that function, and it's going to give me a probability, right? So this is what I have to do when I have a continuous random variable. And this probability density should again add up to 1, right? So it means that when I integrate it from minus infinity to plus infinity, if I just tell you what is the chance that I drop this and it hits somewhere in this class, you're going to tell me the chance is 1. It's not going out of the class, right? So the chance that, or the chance of being any real number is going to be 1, correct? But the density function itself, can it be something more than 1 at one particular point? Yes? Yes, it could be, right? So there is no reason that the integral of one function be 1 and it itself be always less than 1, right? Dirac impulse, yeah? It's infinite at one point, but the integral is always 1, correct? So from now on, I always say distribution, and whenever it's hard for you to think of continuous random variables, just throw it away. This guy is enough for you that is more intuitive, but if you deal with a case where we have also continuous random variables, you know that everything can be just translated into that case by just replacing the mass function with the density function. That's great. So now, if I have one random variable and I put it next to another one, I put all of it inside one vector, it's going to be a random vector. So what is the distribution of that random vector? The joint distribution of every single guy inside that, right? If I collect lots of random numbers, put them in form of a matrix, what is the distribution of that random matrix? The joint distribution of all the entries inside the matrix, right? So when I tell you I have one data x, like right now you think of data as a vector, or later on you might think of it as a tensor, but when I tell you I have a data x with distribution px, you don't wonder how I can define the distribution of a vector or a tensor. It's simply that mathematical object, every single number inside it randomly generated, and when you think of a distribution, the joint distribution of all of them, right? Clear? Great. So that's it, and then we define something called expectation. Everybody knows this notation? What is the expectation of one random variable? What is the expectation of this guy, this binary guy? The expectation of x is going to be, what is it? Please say it. I know everybody knows it. It's going to be 0.5, right? How I compute it? I'm going to look at every single possible outcome. So here is 0 and 1. I get the 0, I multiply it with its corresponding probability, and add it up with the next guy, multiply with its own probability, and so on. So it's going to be 0 times probability of 0 plus 1 times probability of 1, which is going to be half in this particular case, right? So everybody's clear, right? Now, if instead of this x, I just replace f of x, so if I want to compute the expectation of any function of a random thing, what should I do? I do the same thing as before. Instead of putting x here, I'm going to put f of x there, right? So if I have f of x in general, so I can just replace, instead of x here, I put f of x, and everything goes on as before, right? So I know the distribution. I can simply compute the expectation. But why do we call it expectation? Any idea? What is the reason we call it expected value of that random variable? If you have this binary random variable, you have a coin, you flip it, okay? If I flip it 100 times, and I do know this is a symmetric coin, what do you expect to see out of these 100 experiments? 50 times head, 50 times tail, right? 50 times 0, 50 times 1, yeah? And then you would say in average, I'm seeing half, right? 0 plus 1 divided by 2, or 50 times 0 plus 50 times 1 divided by 100, it's half, right? I mean, of course, when you do the experiments, not necessarily half. It could be 0.4 something, right? But if instead of 100, you do it 1,000 times, it's going to be closer to half, right? If you do it 10,000 times, 100,000, and so on, if it goes to infinity, so you keep on doing it till the rest of your life, then at the end of the day, the number you get is very, very, very close to half, given that we assume that the coin is symmetric, right? Clear? So this is why we call it expectation. So it's nothing coming from Mars. It's coming from law of large numbers, right? So I get the coin, right? And each time I throw it, it's a binary thing. It's symmetric, so it's going to be tail or head, 0 or 1, with probability half, half. Next time I do it, I have exactly the same random variable, right? But I do it independently, correct? So what I am doing by just throwing this coin over and over, I'm just collecting what we call it independent and identically distributed sequence, right? I get one random variable, I just realize 100 times the same thing independently, okay? This is going to be IID sequence, and if I have IID sequence and I do know the distribution of that random thing that I'm trying over and over, then what I expect to see as the average after doing lots of experiments, so when the number of experiments I'm doing is going to infinite, if I do compute this average, I do expect it to be the expected value. Everybody's clear? So we're on the same page. Don't worry, I'm not going to just make it super complicated here. So we are going to have very simple analysis, but I just want to make sure that you do get what I'm saying, right? So intuitively. The reason you call it expected value is because if you try so many times that random thing, at the end of the day, in average, you expect to see that, right? This is the reason you call it expected value, right? This is what we call it law of large numbers. I mean, of course, when I just throw one coin once, it's going to be either 0 or 1. So it's never half, right? But if I do it enough number of times, then it could potentially get very close to half. So it's law of very large numbers, so when you try it. So moral of a story, if you do arithmetic averaging on one random process for lots of independent tries, then at the end of the day, you're going to end up with the expected value, right? Everybody's clear? Any questions? Great. So if you got no questions, then let's start with the training of a model. Okay? So let's say what I want to do. I want to get a model, and then, I have this data set. So the data set has some data, x, and then its own label. So I'm thinking of a supervised learning. And then I have I of them. Okay? And what I want to do, I want to find out what is the function which gets x and gives me y. This is the thing that I want to find out. Now, from now on, I'm thinking of x to be one-dimensional, so it's just a number, a scalar. And the reason is that it's going to be easy to show it on the board, okay, in these slides. Everybody's clear? Great. So I want to do that. So x are real inputs. So what I can think of is that my model, whatever it is, so it could be perceptron in the case of classification, it could be a linear model like the dummy example we had, or it could be any polynomial function, anything it could be. So it's a model. It has a bunch of weights inside it, which I am free to choose. And then I want to choose those weights so that when I put one number x into it, I get one y, which is exactly like those things I have inside my data set, right? And then if I can do it very perfectly, I hope at the end of the day that if somebody gives me one new x, which is not inside my data set, I still get the right value for y. Correct? OK, so this is my model. So what I want to do, I want to exactly fit it into my data. Now, let's first think of the model as a function, right? So if I fix this W to one value W1, okay? If I think of the weights, some fixed value, I put all the weights to be 1, okay? Then this guy is a function of, is a function of x giving y, right? Correct? So I can plot it, correct? So I can plot it in this form. X is the horizontal axis, y is the vertical axis. Every single choice of x, I'm going to put it in that function. I'm going to see y, and then I can plot it, correct? You agree? Yeah? So this is when I choose. I need to set w to be something, correct? So I'm going to put w to be w1. But what if I change w to something else? What's going to happen? Sorry? Please say it. It's going to change that function, right? So if I change w1 to, for instance, w2, then this is going to be another function, right? You got the idea? So if I play with, you just think of w as a tap. If I just change it, if I just tune it, then it's like old radios. When you change it, you get into another frequency, right? When I change it, I'm just playing with that function. That function is just going up and down, right? Now, this is what I'm going to have as the model. And now, what I want to do, I want to understand what is the true function g. Now, you might wonder what is the true function here, right? So what do I mean? I mean that I think there exists one function g. That function g is the exact true function, meaning that for every single x on the real axis, if I give it to this function g, it is going to give me the exact true label y. You got the idea? So, do I know that function? Please answer. This is a very crucial question. No, I don't know. I mean, if I would have known this, I wouldn't have done any of this, right? Yeah, I just go home. So I don't know that function, but I can assume, I can think of that function exist, yeah, somewhere in the parallel universe. I don't see it, but I can think of it exist, yeah. You might say, okay, it's not the case in all practical situations, and I do agree, right? But what I'm saying literally is that I imagine there exists one function which is able to look at the pixels of one image and tell you exactly whether it is a cat or dog. Well, we as a human being, we don't know exactly how we do it, right? So I cannot say whether that function exactly exists or not, but I can assume it exists, right? I assume that exists. But what is that? I don't know. Okay? Everybody's clear? So that function is g, and this is the function that every single input that I give to it is going to give me the right, correct label. This is not my model. My model is not doing this. My model wishes to be exactly that function. Clear? Or at least it can approximate it. Everybody's clear? So again, let's plot it. So this is my model, the blue guy. So if I put the weight to be w1, then it is like this. If I put it w2, then it's going to change to that function. And this g function, which I don't know, but I assume it exists, it could be one function like this, right? Correct? Everybody's clear? Great. So now, what I want to do, what is my purpose? My purpose is that play with that w, just tune the frequency of the radio, so that that function at the end of the day goes and exactly line on this true function, right? That model exactly gets changed so that at every single point, every single possible input x, it exactly lies on the function, right? So if I can do that, then that's over. I have done the learning perfectly. I have learned the function, which I don't know, right? So again, here I don't know the function. It's going to sound very weird to talk about this. But let's for the moment assume that this exists and see how we can do this, okay? So in order to quantify this wish, I can use the idea of computing loss, yeah? So this is why I'm calling it pointwise loss. What do I mean by a pointwise loss? It means that think of one particular input x0. Yeah? So it means one single point on this x-axis. Okay? One single x0 here. So if I give it to my model, it's going to give me y hat 0. Right? This is the output of my model. Correct? And if I could have access to this unknown function g, when I give it to that function, it's going to give me y 0. Correct? So I have these two things, y0, y hat 0. What do I want? Y hat 0 to be exactly y0, right? So the loss function is the guy who is computing this difference. So I'm going to put it inside the loss function. So the loss function is computing this difference between y0 and y hat 0. This is the loss computed for the point x0, right? It could be different for another point, right? If I change x0 to x1, it's going to change. So this is why I call it pointwise loss. So I give exact point x0 to both model and the true function, and then this is going to be the loss, the difference between them, right? And this loss depends on my model parameter, right? If I change the model parameter, this function is going to change. Its value at point x0 could change, and then this loss is going to change, right? And this is the only thing I can play with in order to make this loss as small as possible. Great. So now let's just have a bit of visualization. So say this is my model, and then as I told you, I am just looking into one particular point x0 on the axis. Then this x0 is going to hit each of the functions, so the model and the true function at two different points. And the difference between these two guys is going to be the pointwise loss at the particular point x0. I mean, obviously, if I push x0 to left in this particular diagram, this loss is going to just decrease, and on the right-hand side, it could increase, right? So it changes from one x to another, right? Great. So that is it. So what I do want to do, as I said, I want to exactly fit that model to the true function, meaning that I want to make this pointwise loss 0. But how do I want to make it 0? Do I want to make it 0 only at one particular point x0? No. Yeah. I mean, it doesn't resolve my issue if I do it for one point. Yeah. I want this to happen for every single point, right? Any idea how I can do it? Just remember what we did in the dummy example. Some of them, right? If my loss is non-negative, yeah, it's either 0 or positive, correct? And if I sum it up over all possible x's, right, all choices of x, then when I make it 0, for instance, it means that every single point has loss 0, and this is what I want, right? So the correct way of doing it is as if I, where is the other chalk? Come on. Yeah. So the correct way of doing it is that I do it like this. So I'm going to get this loss. I'm going to get this loss, which is a function of x for a given w. And then I just sum it up over all possible x's, right? In this diagram that I showed you, this x is continuous. I cannot do the summation. What should I do instead? Integration, right? So I'm going to take the integral from minus infinity to plus infinity, and then dx, and then I want it to be exactly 0, right? This is what I want, correct? But what if I know, for instance, that, I mean, even though that my model comes here, my true function or my data would never has any x more than 5, for instance. Do I care whether my model is exactly fitting the true function after 5? Do I care about that? No, right? So let them be exactly the same up to 5, but after 5 they just be different, right? It's not going to harm me, right? Now, if I do know that this x is happening with some particular density px, then it makes sense that I get that density, I multiply to the share of loss, and then I do the integral, right? if the density is 0, that part of the story is never going to happen, then I'm not going to just try to minimize it. I mean, it doesn't make sense. Everybody's clear? Did you get the idea? Everybody's clear? I mean, if it's that clear, so just say yes. Great. Okay, that's great. So this is exactly what we do in the Bayesian sense. So when you say Bayesian sense, it simply means that because Thomas Bayes was always looking at the problem from this point of view. What is the frequency of x happening? I'm going to multiply it into the loss because this is also important. I don't care that the model exactly fit into the data, true function all the time. I only care about the region where my data exists there. Okay? So this is the whole idea. So I cannot do it, as I said, for one single x, 0, but I should do it for everybody. So the way that I do it, I assume that every x is happening with some density or probability px0. And then the thing that I do, I am going to compute this integral. And this integral is nothing but the expected value of that loss function. Clear? Meaning that I think of my data to be a random variable. That random variable, that random data, is happening with some probability at every region. And then I say, this is the true function, this is my model. I compute the loss between them, and I try to make it in average 0. If I make it in average 0, then hopefully it's going to make, or if I make it a small in average, then it's going to be small for every single output of my data, every single image that I see. So you got the idea? Was it very complicated? So congrats, that's over. That was it. Okay? So now, this is what we call it risk. And the whole training gonna be to minimize this risk. Okay? So the whole idea of training is that I minimize the risk, the difference between my model and the true function. So I'm gonna say, this is the model, this is the true function. If I do the integration, I am going to just integrate everything in this distance between them. But if I do know that my data is most of the time here, and here it's not going to happen, so I don't need to care about this. I only need to focus on this part, right? So I'm going to just multiply the distribution of my data to that loss function, and then I compute that risk. And the whole training is going to minimize this risk function against all possible choices of W, right? Because that R is only depending on the weights now, correct? So once I do this expectation here, once I compute this expectation, this x is going to be integrated over. It's going to disappear, right? And the only thing remains is the parameters that you can play with, right? And then you want to just solve this optimization problem. You want to minimize it. But can I compute this risk function? Can I do that in practice, in reality? That was a nice mathematical model, but can I do it? No, I cannot. What are the things that I'm missing? The probability function, exactly, the density function, or the distribution in general. What else? G, the true function, exactly. So I neither do the true function nor I know the distribution, right? So I cannot compute that. That sounds like a kind of, silly mathematical model only, right? But using law of large number, I can do it. Why? Because, in fact, those points that I have inside my data set are samples taken from that imaginary function g, right? Because I do know that inside my data set that the label for xi is yi, meaning that if I had this function g in reality and I give x1 to it, it's going to give me back y1, right? So if I give x2 to it, it's going to give me y2, and so on. If I give xi to it, it's going to give me yi. So those points inside your data set are nothing but the samples of that true function, right? So you don't know the function, but you know its samples, right? And you know the samples, you want to approximate or you want to estimate some expectation. What should you do? You just use the law of large number, right? You compute the arithmetic average, and you hope that that one is the expected value that you want. It's not going to be the exact one, but if you have a lot of data, it's going to be the same thing. So in sense of this problem, so I was talking about the pointwise loss. I can compute this pointwise loss for every single point inside my data set. Because for every single point inside my data set, I can pass it through my model, so I'm going to see the output of the model. And I do know the output of the true function because it is the label which I have inside my data set, correct? So for every single point inside my data set, I can compute this loss. Everybody's clear? So now what I can say, even though I don't know the distribution, but if I give every single point inside